We're now going to start heading toward a new algorithm problem. But before we do that, we're going to look at representing walks as something called multigraphs. So first we're going to demonstrate how some walks can be represented as graphs. We're going to define multigraphs to help us represent walks that can't be represented by graphs. And then we're going to describe the problem that we're really heading toward, and that's called the route inspection problem. So suppose you have a graph that has the following walk. So it starts at V1, goes to V2, V3, V4, V5, back to V3, back to V1, and then to the V5. Now this may not be all the vertices in the graph, but this is a walk within the graph. How might you represent this walk as a graph? Well, it's pretty straightforward actually. You start with your 5 vertices that are in the walk. Again, these aren't all the vertices that are in the graph necessarily, but they're in the walk. You start at V1, you draw an edge to V2 because you know you're walking across there, then to V3, V4, to V5, then you go back to V3, and you go back to V1, and then you go all the way back to V5. Now we know all these vertices and edges are in the graph, but they're not necessarily all of them. So it does not necessarily represent the entire graph G. But it does give some perspective on the structure of the walk, and in a way that's going to be helping us when we solve our route inspection problems. Now, what if you have a walk like the following? It goes from V1, V2, V3, V5, V4, V2, V1. Well, we travel along V1, V2 at the beginning, and then at the end go back from V2 to V1, which means that we're traveling twice along the same edge. How would we model that in a graph? Well, we can try doing the same thing we did before. We start from V1, you go to V2, then to V3, then skip over to V5, then back to V4, and back to V2, and then back to V1. Now notice what we did here is we have for lack of a better word, we have a graph with 2 edges between V1 and V2. The problem is that graphs don't let us have more than one edge between vertices. So we need to define something else. And that something else is going to be called a multigraph. So a multigraph, it still has a pair of sets V and E, where V is a set, that's our vertex set, and E is our edge set. But our edge set now allows that we may have more than one edge between a pair of vertices. So now if we have the following multigraph, well, it's perfectly fine. It's not so great as a graph. Graph only allows a single edge at most between 2 vertices. This one has multiple edges. It's perfectly fine for a multigraph. This could represent a walk where we walk twice between V1 and V2, V2 and V3, V1 and V4, and V3 and V5, right? We walk twice between V1 and V3, and then 3 times between V4 and V5. And a particular walk that could possibly represent, not the only one obviously, is the following, where we start at V1, then we go to V2. Look, I turned that one blue for you to show you where we are in the walk. After V2, we go to V3, then we go over back to V1, then we go down to V4, over to V5, back to V4, back to V5. We're having fun going back and forth between V4 and V5, up to V3, and then back to V1 to finish them off. And notice that every edge has been used, in the multigraph has been used exactly once, which is exactly how we wanted to have it. Now, representing walks as multigraphs can be useful in problems where we're trying to find some walk that is optimal in a certain graph or maybe a weighted graph. And the particular problem we're going to be looking at is something called the route inspection problem. So what is the route inspection problem? Well, we start with a weighted graph G, and the question we ask is, how do we find a walk that satisfies the following properties? We want to make sure we cover every edge in G. We want to make sure that wherever we end, it's at the same vertex where we begin. So that is another way of saying that is it's a closed walk. And we want to make sure to do this as efficiently as possible. And efficiently to us means the total weight of the walk is as small as possible. And I want to be very clear what I mean by total weight of the walk. That means we add up all the weights of the edges that we crossed in the walk. And if we happen to cross an edge more than once, we count that weight the number of times that it's crossed. So in other words, if we cross that edge 3 times, we add that weight in there 3 times as well. So we're going to go ahead and explore how to use multigraphs to solve this problem in the in-class activities. So now I think you're ready to work on the first set of problems that we have for root inspection. It's called Introduction to the Root Inspection Problem. I want to note that those activities are mainly to sort of build understanding about how our algorithm is going to work. It will not be included on the quiz, but it is a good idea to look at those to get you ready for the more difficult problems ahead.